delta n. Here both the m and delta, m and delta n are functions of n.
Hold up, so please press the OK. I'm sorry. The right point from top OK.
Yeah, the blue one. Okay. So the degeneracy of the ground state is bounded by a finite integer n, and that gap between the ground states, and the first excited state is also bounded. So whatever the value of n is, there is also always a finite gap. That's what we're talking about between the ground state and the first excited states. That's one condition, and the other one is if there are, as n goes to infinity, there are finite number of lowest energy states, finite number n of lowest energy states, which have an energy separation epsilon among themselves, which is exponentially small n. So as n goes to infinity, they grow exponentially small, and the energy separation between these lowest energy states, which are separated by an energy scale epsilon, and all the other states are bounded by a finite number delta for an arbitrary n. So I think a picture might help. So I also so if you consider the first case is when the epsilon is 0, the epsilon here is 0, so all the ground states are degenerate, but the degeneracy of the ground state is upper bound. That is, it can be the degeneracy is upper bound, finite upper bound, and the gap between the ground state and the first excited state is also lower bounded, so it can be lower than a certain finite positive number. This is one condition of the gap, and another one is the finite, as I said before, the lowest energy states are not degenerate, but they are separated by a energy separation epsilon that goes exponentially small as we increase n. So as we go to a thermodynamic limit into infinity, they are effectively degenerate, and all the other states are separated by these lowest energy states by a finite energy gap delta. So that's okay. I have an example here. So this is the transverse Ising model. So we are considering the B here. We can consider B as the magnetic field. So we can apply a magnetic field along the x direction, and we're also considering coupling of the z component of the spin, nearest neighbor coupling of the z component of the spin, and it can be calculated. I'm showing the calculation here that this Hamiltonian is gapped unless J is unless J is equal. I think it's unless this is not correct. If J, it should be if gap if J is not equal to B. So when if J is equal to B, then the Hamiltonian is gapless. Otherwise, it's gapped. When the value of, in particular, there are two cases. So J equals B is the kind of point of phase transition. Before that, when J is greater than B, the ground state degeneracy is M equals 2 . So there are two degenerate, ground states, and when J is smaller than B, the ground state is unique non-degenerate one. So in particular, we can consider the case B equals 0. In that case, the ground state is the ground space is spanned by the tensor products of this eigenstate of Z spin operator, and the two eigenstates of the Z spin operator. And when J is equals 0, in here we can see that it's just the B, the second term. So it will be just the eigenstate of the X what is it? X component of the spin operator, which is just this thing plus eigenvalue of XG. And I think this would be more of a demonstration how this works. So as we said before, when J is not equal to B, we will have gap, and when J is equal to B, we will not have gap. So let's see if that's the case. So A and B are the energy, A and B. These are all the energy spectrums of this transverse Ising Hamiltonian, and particularly we are considering these four configurations. The A is when we go to B here, and we're considering 8 sides. In that case, as we can see, we can see that obviously we can see that here, but here the ground state has 2 degenerate states, and there are other states here, as you can see. And when we increase the number of sides from A to B, when we change, if we now consider B, here we have the same J and B value, but where we increase the size from 8 to 16. In here, I mean, it's not it doesn't prove that it's gapped, but I mean, it seems pretty convincing that there's a finite gap between the ground state and the cross excited state. So, and for C and D, the J and B are equal, so we expect no gap. And as we can see, as the size n is increasing from 8 to 16 in C and C to D, the gap between the lowest energy states and the second lowest energy states are decreasing. And okay. So the next topic is correlation, and correlation, I mean, in a manual system, we consider the correlation between two operators that act in finite regions. So if O1 and O2 are operators acting on finite regions R1 and R2, that's the consequence of locality, that we're considering only the interaction between particles that are between a certain length scale. And we define the correlation function between O1 and O2 defined as follows. We take the average. What we mean by average is, I will explain it. Average of the product of O1 and O2 minus the product of the average of O1 and O2. Here, by average, we mean the expected in zero temperature, we are taking the expected value in the ground state, but in finite temperature, we're actually taking the expectation value in the thermal state. So we have to do the whole partition function thing as well. And this is actually inspired from the correlation function of two random variables, x and y. So the correlation function of two random variables x and y can be defined as follows: that here ex and ey are the expression values of x and y, and exy, the first term is the expression value of the joint probability distribution of x and y. So as we know from our probability class, that if x and y are independent, if and only if this correlation function is zero. So that's the thing that inspired this definition. And why did I mention that? Because in a gap system at zero temperature with a unique ground state, the case where the ground state is non-unique is a bit complicated, so I'm just skipping that. And when the ground state is unique, all correlation functions of the ground state decay exponentially with R. So the any correlation function would be exponential decay, and we consider this because epsilon is called the correlation length of the system. On the other hand, if the system is gapless, for example, a system with a Conformal surface, okay, let's ignore that for now. If the system is gapless, however that might be, the correlation function in the ground state decays polynomially with R. So with alpha, obviously alpha is greater than zero, and in that case, since any polynomial functions decay slower than an exponential function, we say that such gapless systems have infinite correlation lengths. And finally, our final property of the quantum many-body state is the entanglement. And if you recall from the entanglement of two-body systems, it was that or two bipartite, in particular, if I'm precise, then I'm talking about a bipartite state, which is any state of the any state can be written as the product of the Hilbert of the state of the two different parts. So if that's the case, then we can define an entanglement measure SAB, which can be either calculated on the part A or the part B. And here rho A is the density matrix where we have trace of the B part, and here rho B is the density matrix where we have trace of the A part, which is the mixed density matrix, if I'm not wrong. So in many-body systems, we usually focus on the entanglement entropy with a bipartition of the system. So we usually consider when we talk about the entropy of a many-body system, we usually talk about the entropy when we consider the when we divide basically when we divide the system into two parts and consider the entropy between them. And of course, since we're talking about many-body system, we take the limit of both of the parts go to infinity. And in particular, we're interested in the scaling behavior entanglement of the systems. So we're talking about how this entanglement of the system is changed when the how that depends on the size of the system. So all that discussion we did is for this entanglement area law. So this entanglement area law is here as follows. If the system here is gapped, okay, here we are talking, I should talk about system first. So let's consider a 2D lattice with sites on each 2D lattice with infinity big 2D lattice. And if the system is gapped, that is the Hamiltonian that's governing the system, its spectrum is gapped. However, that might be one case would be the Renormalized Ising model. Okay, yeah. Then the many-body entanglement that we discussed defined before in the ground state, it says as the entanglement area law. So one like rough estimation of such entanglement should be like since there is the degree of freedom of inside the area A scales like L squared. So the entropy should scale like L squared as well. But as it turns out, and that's the case if we abandon the condition of locality. But since we're considering locality, we should the entanglement is the calculation of the entanglement turns out to be a bit different. And as it turns out, when we're considering the gap ground state, I mean, when there's a gap in the spectrum, the entanglement entropy always scales like L. And okay. And so the entanglement area law, if we state formally, it's as follows. For in particular, when we're talking about a system in 2D, we have the entanglement scales like L with a scaling coefficient, obviously. And in general, in a d-dimensional system, obviously we're talking about a gap system. The entanglement should scale like into the dimension. So basically, it's the generalized version of this thing, in a 2D thing. So if we consider in 3D, the entropy should scale as an area, and that's what the name area comes from, because here the boundary between A and the outside is the surface, and that's what the entropy scale as. And in 2D, in one dimension, it is bounded by a constant, because the boundary is just 2 points. So, and this law, there should be a quote here because anyway, this law can be from a thing that we discussed before, like as we discussed here in correlation, that the correlation of such quantum mechanical systems, that when in a gap system, the correlation goes, it exponentially decays with the distance. So the entanglement should be very local. So when we're considering the entanglement between A and the rest of the system, the most of the entanglement, or how do I say, interaction that's contributing to the entropy is around the boundary of the system, and this boundary scale as the area, or a to the power d minus 1. That's where the entanglement area law comes from. And in 1D system, this area law has been put as a mathematical rigorous theorem. So you can check those here. Even I don't understand how those work. But in higher dimensions, there doesn't in dimensions higher than 1, there doesn't exist any proof yet. But there are like tons of mathematical numerical calculations being done, and it's been proved, quote unquote, a lot of times in many literature. So that's the entanglement area law. But when the system is not gapless, when the system is not gapless, the entanglement area law fails. That's one. But before that, we will talk about the topological entanglement. That is when the system has non-trivial topological order. I'm cheating a bit because I'm not properly defining the term topological order, but let's go. For when a system is gapped, we're still talking about a gap system, but the system has non-trivial topological order. So it might be the case that the Hilbert space is the topology of the Hilbert space is not anyway. I'm gonna fail in doing that. So if the system has non-trivial topological order, then the entanglement entropy of a region, like we calculate in the same way as we did before, but the calculation found when we did the calculation, we found out that the area law is still works, but we have to add a constant term to the expression. So the result that comes out is when for a topological ordered system in 2D, the entanglement expression contains a negative constant term, and we call this negative constant term as the topological entanglement interval system. And okay, I'm really, I don't know, I'm guilty of that. I'm not very well. Anyway, this term comes from the non-trivial, like this non-trivial topological order that I'm not obviously explaining. This leads to interactions that are not necessarily local. So the locality condition that we were assuming before is now violated to some extent, and that's where this constant term comes from. And okay, this is like another level of cheating, but anyway, for example, we can see the toric code, the Hamiltonian and toric Hamiltonian, and I can briefly explain what it is. And so basically, we are taking the z terms of the z component of the spin, and x terms of the x component of the spin, and the first term is the we are taking the product of okay, this is not the product of the spin terms, the z spin z terms of this star spin. So what we're doing is So let's take this is one of the star shapes that you can find in this square lattice. So we are taking the product of these four in Z terms, and we are summing up on all the star terms. And this is the placket. Placket is like the star term are like this, that doesn't lie on the, this unit square, but the placket terms, they lie on the unit square. So we are like the first term, we're also taking the product of the four spin X terms that are on this placket. They were taking the product of these four terms and summing over all plackets that are present in the toric code. Okay, I don't think that that's one, but anyway. And it can be shown, and I'm not doing that as well, but it can be shown that when the density matrix of when we consider a small an area A of this square lattice, and and the size of the area is L, then the density matrix is for the region A is an equal weight mixture. So all the states have equal weight here in this density matrix of the 2 to the power L minus 1 eigenstates. So so in the base of these eigenstates, this density matrix looks like a diagonal matrix. So we can just take the we can just evaluate the entanglement entropy simply, and as it turns out, it's just L minus 1 log 2. And from our definition of the topological entanglement entropy before, this topological entanglement entropy for the toric code turns out to be log 2. And finally, the area law is also validated in gapless systems. So the system, the Hamiltonian, where the gap is not present, but the validation is not as strong as the topological entanglement entropy. It is usually modeled by a term log L. So, for example, an example that I don't even understand, just mentioning here, is that for one-dimensional critical points that are described by conformal field theory, so this is like these are proved by high energy theory guys in the 90s, that in such one-dimensional CFTs, the entanglement is so. If you recall beforehand that the entanglement entropy for a gapless system is just bounded by a constant term, but in here there is a log L term here, so the entanglement entropy in this case is bounded by a small log term. So, and in another case, for a gapless pre-Fermion system, so we're talking about no interaction, just creation and annihilation operators. In that case, and if the system is gapless, in a d-dimensional system, the entanglement entropy scales as a to the power d minus 1, so with a constant term as well. But there is also a log term here. And if you recall before, in the entanglement area log had just the d minus 1 term, a to the power d minus 1 term, but here this is modeled by a log L term. And the physical interpretation of this thing would be that since the system is gapless, the ground state there is in the thermodynamic limit there is effectively no energy gap between the ground state and the excited states. So the excited states can carry that correlation on the ground state, so we can have some penetration of entanglement beyond the boundary. So that's what the log L term comes from, but it's still bounded because even if the system is not gapped, then we are still talking about local Hamiltonians. So it's still bounded by loosely by a local term. So finally, okay. So I'm gonna summarize what I babbled about in the last 30 minutes. So entanglement measures in gap system, if we are talking about a minimal system here, of course, they follow a so-called area law. That is, the entanglement usually scales with the area between the region where constant number and the outside. And so in 2D system, it's linear. In 3D system, it's going to be an area L squared and so on. And this area law might be violated in two different cases. One is when the system has non-trivial topological order, and another is when the system has no gap. So when the system has non-trivial topological order, we have an extra constant term in the area law that we call the non-trivial entanglement entropy. And when we have no gap in the system, then usually, I mean, these are not true. Like for one thing, the area law is an rigorous mathematical theorem at least in one-dimensional system. But these are not, at least the entanglement in gap systems are not a universal law. So, but in most cases, they are mildly scaled by a logal term. And why am I even talking about this thing? I mean, why do you care about this? So because this entanglement measures, I mean, entanglement entropy or any other measures, I mean, not all systems you can consider the entanglement entropy. We might have to consider some other measure of the entanglement. But anyway, whatever entanglement measure we're talking about, it can be used to detect phase transition, especially in the cases where conventional approach of phase transition, that's like the things that we learn in statistical mechanics, like order parameter. Like order parameter is the guiding thing in the classical study of phase transition. These things, when these things fail, particularly when you have topological order, but entanglement measure still work in those cases. So that's why we care so much about these things. But even if it's useful, it's not usually very easy to calculate the entanglement measure in most cases, but it's an improvement. So yeah, that's it for my talk. If anyone have any questions, please. Okay.
So could you give us an exact example or some kind of like what kind of materials gives what kind of phenomenon, and those phenomena cannot be like detected like conventional probes, but we can deal with these kind of matters.
And you mean these?
Yeah, some kind of like specific kind of example. Could you?
I mean, in particular, when we have like topological insulators. Topological insulators topological insulators usually have non-con like you can see in the band structure that it doesn't have the usual how do I say conventional phase. I mean, the phase are topological phases, and the transition between those two phases or many phases can be, you can like probe those using the order parameter that we usually do for, let's say, when we're talking about the phase transition between ice and water, because those interactions are local. That's why an order parameter is a local thing. That's why those things work in those cases. But since the topological phase is not necessarily a local thing, it doesn't really work well if you try to apply the order parameter. But to answer your original question, like, so where do we observe topological phases, right? Yeah, you mean this topological phase transition. So one example might be graphene. Graphene calls, like, in graphene, we usually observe. I think not like the usual natural graphene, but people have like engineered like with graphene, and they make very weird interactions. Like there is a like holiday thing, a holiday term in those things. That people somehow, I don't know how, but people engineer those Hamiltonian real materials, and those show its topological phases.
Thank you. Isn't there's one question in the Zoom, so maybe
Can I have? Yeah, sure.
yeah. Maybe yeah. Maybe still typing.
Okay. Okay. In a calculus system, it sense that okay. Long read. In a sense that it is by t, which should scale with volume instead of area, given the long correlation length and the expectation that in however the volume. Okay. I mean, in a gapless system, I mean, even when you're talking about gapless systems, the Hamiltonians that are considered in quantum many-body physics are still local. The only difference is in the thermodynamic limit, there is no gap between the ground state and the excited states. So, and in that case, the how do I say, non-correlation in the gap system, the non-correlation is very strong. It goes exponential, but in the gapless systems, the non-correlation, I mean, the how the two systems are not correlated as there is not as strong as exponential, but it still decays polynomial. So the correlation length is longer, but it's still, not infinite. I mean, okay. This is like I said that correlation length is infinite, but this is just convention. I mean, how do I say? The correlation decays. It does decay. So that's where this log L correction comes from. I mean, the correlation decays. So when two regions are close together, there's going to be like more entanglement. I'm talking loosely here. More entanglement among them compared to regions where they are far away from each other. So obviously the entanglement is not going to be scaled as volume. as you're suggesting, right? Because if that's the case, then there is really no difference in entanglement, whether the two regions are closer together or farther apart. So I guess that's my answer. I think the infinite correlation length is a bit misleading. And I guess people use it for different reasons, maybe useful in some cases, but infinite correlation length doesn't mean that, you know, correlation is the correlation doesn't depend on the distance. It does depend as the distance became bigger and bigger. Yeah, okay, there's so much did it. Including the understanding the block term that because of decrease and including the understanding the log term that because the decay of the correlation length has changed from the conventional exponential scale to I think so, but I'm not so confident about it because the the major result with this thing comes from the CFT result, and well, I don't really understand it. So, but intuitively, even from my intuition, I also think that this is a correct interpretation.